Hello friends, you are welcome to the GMAT 41's elementary mathematics class. In our class today, we are introducing the topic partial fractions. In the previous class, we treated polynomial. We're going to use certain concepts of the knowledge you have there to see how we work on partial fractions when necessary. However, what do we mean by partial fractions? Partial fractions refer to two or more single fractions obtained from splitting complex or algebraic fractions. Let's quickly take our mind back to what we may have learned in addition and subtraction of fractions. I'm going to start with natural numbers, perhaps. Imagine you're given 1 over 2 plus 2 over 3. You have to add these two fractions. Usually you go through the LCM of the denominator, where in this case, the LCM of 2 and 3 is 6. Of course, you're going to multiply the two of them because 2 cannot divide 3, 3 cannot divide 2, and no number is common to the two of them. So the LCM will be 6. Write up the 6 here. Then you will do this LCM 6 divided by the denominator of this fraction. 6 divided by 2 will give you 3. 3 times the numerator 1 will give us 3. And then plus 6 divided by 3, you come to the second fraction, you get 2. 2 times the numerator 2 will give us 4. And you see that eventually this will give us 7 over 6 if you work it out. Which simply means that 1 over 2 plus 2 over 3 is equal to 7 over 6. Now I'm going to ask you a question. How about someone requests that you work this 7 over 6 back to 1 over 2 and 2 over 3? What do? This is actually the concept of partial fraction, whereby you break down that complex fraction into two or more simpler fractions. But take note that in partial fractions, our focus will be on algebraic fractions, not just natural number fractions. Is that okay? Algebraic fractions, those that contains alphabets. Alright? We'll be consistent with using x as the case might be. Please, look at this instance on the board. Assume that you are asked to add up these two simpler fractions, 1 over x minus 1 plus 2 over x minus 2. In working out this, one can choose to say, okay, fine, let me use LCM of the denominator. Where in this case, the LCM of x minus 1 and x minus 2 is x minus 1 times x minus 2. You're going to multiply the two of them. And then you would do this denominator divided by, you come to the denominator of this fraction here, which is x minus 1. So this LCM here, divided by this denominator x minus 1, of course, if we cancel this x minus 1, x minus 2 will be left. Use the x minus 2 to multiply the numerator, just like I explained up here. And that's going to give us x minus 2. Then your sign here is plus, you put plus. Again, this LCM divided by the denominator of the second fraction x minus 2. The x minus 2 will cancel this x minus 2 to leave us with what? This x minus 1, which will multiply the numerator here. And of course, if it does, we're going to have 2 bracket x minus 1. Work out the numerator here and see. Open up this bracket, you have x minus 2. Open up this bracket, you have 2x minus 2. And then add up like terms. X plus 2x will give us 3x. You can see that, right? And then minus 2 plus minus 2 you have here will give us minus 4. So do you see that these two fractions on addition gave us this single fraction? But this single fraction is complex in the form. It's complex because you can see in the numerator you have more than one term, and then in the denominator, even the fraction or the factors you have in the denominator being multiplied makes the process more complex. Is that okay? It makes this term more complex for us. Now, it is possible for you to reverse what you did to get this result here. That is, working back from these complex fractions to get these simpler fractions. And that process of splitting this complex algebraic fraction to these simpler fractions is what we refer to as what? Partial fractions. In fact, each of these simpler fractions we obtain are known as the partial fractions of this complex algebraic fraction. Do you know something? Partial fraction is a simple one. Is that okay? Now, there are some basic key concepts that you should know. One of them is, in order to obtain partial fractions from a single algebraic fraction, it involves certain process. And this process that it involves depends on the type of partial fraction produced. You see, every complex single fraction can produce its own partial fractions. Now, the type of partial fractions that the complex algebraic fraction produce, just like in this case, this produces this partial fraction, the type of partial fraction that this complex algebraic fraction will produce depends on the denominator of this complex fraction given. Take note of that. It depends on what? The denominator. Now, we are saying that the type of partial fraction it produces will depend on what? The denominator of the partial fraction. So look at how it links. The process you apply depends on the type of partial fraction produced. That type of partial fraction on its own depends on what? The denominator of the complex or algebraic fraction you are trying to break down into simpler one. Please, this concept is very, very important. I repeat that again, that the type of partial fraction you produce depend on what? The denominator in the given complex or algebraic fraction. So that when you're given a particular algebraic fraction to deal with, I want to obtain the partial fraction. You want to formulate the partial fraction depends on the denominator. So the denominator is of serious concern to us. Note, to formulate a partial fraction, please, the degree of the denominator must be greater than the degree of the numerator. We've already explained what degree is in polynomial. Alright? So the degree of denominator must be greater. See, I underline it. Must be greater than the degree of the numerator. In a case where this is not true, or in a case where the degree of the denominator is either equal to that of numerator or the degree of denominator is less than that of numerator, you must carry out polynomial division and divide until the degree of the numerator, which happens to be the remainder in that case, will now be less than the degree of the denominator before you can start formulating your partial fraction. In the next video, we shall introduce types of partial fraction dependent, like we said, on the denominator in the given complex or algebraic fraction. And of course, we're going to solve that to see what we are going to obtain. In this video, we now want to focus on the type of partial fractions. Like I stated in a previous video, dependent on what? The denominator. Please, I'd like to state this in a clear term. The way you learn this partial fraction, the types, is simply the same way you are expected to learn the first 20 elements. Is that okay in chemistry? There is no general format. That okay, this you have to follow the format given and then you memorize hydrogen, helium, lithium, beryllium. Is that okay? So coming to partial fraction, what determines the type of partial fraction you're going to form is the denominator. However, that this is how you arrange it or whatever, you have to learn it consciously based on my explanation and what you're going to say on the GMAT 41 board. Type 1. Factorizable quadratic denominator of the form ax squared plus bx plus c, or ax squared minus c squared. This ax squared minus c squared, this c squared is a perfect square. So it's a case of difference of two squares. Is that okay? Once a quadratic expression can be factorized, we assume that okay, the factors will be x plus minus alpha and x plus minus beta. Is that okay? These concepts have been introduced in polynomial in our previous topic already. Once the quadratic denominator is of this type which can factorize, as an example, look at this, numerator divided by, so these are the factors, linear factors of the quadratic denominator. The partial fraction that is going to be produced, I've used blue marker to write them on the board. It's simply a over 1 of the factor plus b over the second factor. So, do you take note of something here, right? I have to introduce certain constants, a and b. They are arbitrary constants. No one told me to introduce it. There is no rule that this is what you must use as a constant. So, you can decide a constant to use. An alphabet, is that okay? The only thing is, once you introduce it, it's now left for you to solve and obtain the value of a and b. Is that okay? Now take note, if this denominator, the linear factors here are up to 3 terms. Of course, if they are up to 3, it means that this becomes what? A polynomial of degree 3. Just imagine we have x plus minus alpha, x plus minus beta, x plus minus gamma. Then this would produce 3 partial fractions as well too, where the third one will be c all over x plus minus what? Gamma. Anyway, I had to focus on this because we talked about factorizable quadratic. For quadratic, there are 2 factors. This case of ax squared minus c squared is something like this. Imagine you're giving x squared minus 1. X squared minus 1 is difference of 2 squared. That 1 is the same as 1 squared. Is that okay? And so the factors that this x squared minus 1 will produce will be x minus 1 and then x plus 1. And you factorize that, you use it as a denominator. Is that okay? Just imagine also you're giving 4x squared minus 9. This is also difference of 2 squared. That 9 is a perfect square. That 4 is a perfect square. You can actually break this thing down to 2 squared x squared minus 3 squared, which if you factorize, you're going to get 2x minus 3 and then 2x plus 3, which will now become the factors to use, the linear factors to use. Please, let's quickly look at this example. 3x minus 4 all over x minus 1 and then x minus 2. Now, an examiner, instead of simplifying this for you, giving you the factors, might simply give it to you such that, you see these factors are the same as expanding it, you have x squared minus 3x and then plus 2. That was what was factorized to give us x minus 1 and x minus 2. Is that also? So once any quadratic denominator is given, you check whether you can factorize first. If you can factorize it into linear factors, and then you formulate your partial fraction. Did you see this, right? Once again, my arbitrary constant, I chose a and b. So it's a all over one of the factors, x minus 1, and then plus b all over the second factor, x minus 2. There is no rule that b must be the numerator of x minus 2. I can choose to bring b here, become b over x minus 1 plus a over x minus 2. Is that okay? Now let us look at type 2. If the denominator is a non-factorizable quadratic denominator, for example, ax squared plus bx plus c, where these cannot be factorized, or ax squared plus c squared, or ax squared minus c. Take note, this c squared here, don't confuse this ax squared plus c squared with this ax squared minus c squared. Don't confuse it. Why this can be factorized? Because it is difference of two squares. This can't be factorized because of this plus. Is that okay? So even if this is a perfect square, it can't factorize. This one also cannot factorize because I am considering that c here is not a perfect square, even if it's carrying minus. Just imagine you have something like x squared minus 3. 3 is not a perfect square, so it can't factorize. Or maybe you have 2x squared minus 5. 5 is not a perfect square, so it cannot factorize. Now look at the partial fractions that we have there. What is the interest, the focus there? Did you take note that the numerator is ax plus b? Ax plus b. That is how it's being presented. Is that okay? So the numerator of the partial fraction you're going to formulate will be ax plus b. You can use cx plus d. You can use bx plus c. You can use dx plus e. It's your choice. Then divided by that quadratic denominator that cannot factorize. I must state this that in practice, when a question of this kind is given to you, they usually would not just give you the denominator of this type alone. They will attach it, with another type of denominator. That way, when we solve questions, you would get to understand what I'm saying better. As an example, look at x plus 2 all over x squared plus 2x plus 7. If you look at the denominator, it cannot factorize because there are no two numbers, no two factors of 7, which if you multiply, you get 7 and then add them to get these 2. No two such number. So this cannot factorize. Therefore, the partial fraction is what? Take note of the numerator, ax plus b. If I want to use bx plus c, it's my business. If you want to use yx plus z, knowing that y and z are the arbitrary constants you introduce to find their values, it doesn't concern anyone. It doesn't concern the GMAT 41. Is that okay? So at the end of that, you now simplify and solve, alright? But let us assume that really you are giving this particular thing, only this denominator. I said something that in practice, most time you cannot just be given a non-factorizable quadratic denominator, all alone like that in the question. They usually attach it with another denominator. But let us assume that you are given just that denominator, non-factorizable quadratic. Nothing else is being attached. It's a simple one. There, once you formulate the partial fraction, look at this. This denominator will cancel this denominator. I hope you know that, right? Then I have x plus 2 equal to ax plus b. Compare both sides. Coefficient of x here is a. It will be equal to coefficient of x here, which is 1. So a will be equal to 1. Then b here is the constant term. It will be equal to 2 here, which is the constant. It does not contain x. Is that okay? So as simple as that. Type 3, repeated factor denominator of the form ax plus or minus b all raised to power n. N must be a positive integer greater than 1. Look at it. N must be greater than 1, and it's an integer, a whole number. What will be the partial fraction? You can see that numerator divided by that repeated factor. How do we know it's a repeated factor? Because of this power outside the bracket. In formulating the partial fraction, it's simply a all over that same denominator from the question raised to the power n. Then plus b all over that same denominator, this time around you minus 1 from the power, plus c all over that denominator, this time around you minus what? 2. You continue until you have the term inside the bracket without the power n. You can see the last term there. Let's quickly look at an example. 2x plus 5 all over x plus 2 all in bracket raised to power 3. Here n is what? 3. And so the partial fraction is a all over that same denominator exactly. That's x plus 2 all raised to power 3. Then plus b all over, this time around the denominator, you're going to subtract 1 from the power. So you can see it become power 2. If you subtract 1 from this power, 3 minus 1 will give you 2. Then plus c all over x plus 2. You notice that there is no power here anymore apart from 1, just like you have this. The power here is power 1, like you have power 1 here. Because if you subtract 1 from these two, you'll be left with x plus 2. Just the term in bracket here without the power there. So the last power is always power 1. Is that okay? Then you stop and solve the partial fraction. In the next video, we are now set to solve questions. It is true that we have a general method of solving partial fraction. However, for the purpose of this course, the GMAT 41 is introducing to you the Omakers denominator closing method and the Omakers numerator free value method. You're welcome to our very first question on the partial fraction. Now on the board we have this question. We have to resolve 4x plus 9 all over x squared minus x minus 2 into partial fractions. Now henceforth we are introducing test your zone of proximal development to our studies. Is that okay? Now when we are done solving this question, you have to test how far you've gone. You will test your zone of proximal development using this question. So you solve to see if you can get your answer. Is that okay? Now, how do we resolve 4x plus 9 all over x squared minus x minus 2 into partial fraction? The first thing is to look at the denominator. Look at the denominator. Already, if you say this, the degree of the denominator is greater than that of numerator, so we don't have any issue with polynomial division here. Is that okay? So we can formulate our partial fraction straight if need be. Now we have to check if the denominator can factorize because it's a quadratic denominator. So I'm going to look at that, and then to test whether a quadratic expression can factorize, we can actually use this part of quadratic formula to find out. Once you substitute for a, b, c here and you get a perfect square without minus sign, it means that that quadratic expression can factorize. However, we can still do this in our own way. How? Look for two numbers which if you multiply, whether you can get minus 2. Ordinarily, the quotient of x squared is 1. You are meant to use that quotient of x squared here to multiply this minus 2. So that in case if this is maybe 2 now, you're going to do 2 times minus 2, you get minus 4. Are you following, right? Before you find the two factors of that minus 4, which if you add, you get quotient of x. Now in this case, the quotient of x squared is 1. 1 times minus 2 will give you minus 2. So you look for two factors of minus 2. Two numbers which if you multiply, you get minus 2. That must also be added to get the coefficient of x here. The coefficient of x is minus 1, is that not so? Now this is where your knowledge of multiplication table is extremely important, you know. Irrespective of the level of learning of a student, I always advise the student, make sure you learn your multiplication table. At least from 2 times to 9 times table can do. Is that okay? So I'm urging you people to do that, please. Alright, now this can factorize. The two factors that will do this for us will be minus 2 and plus 1. Minus 2 times plus 1 will give us minus 2, which is all we have there. And then minus 2 plus 1. That is, you're adding the two together, you get minus 1, which is the coefficient of x here. Therefore, this can factorize to 4x plus 9 all over x minus 2 and then x plus 1. At this point, I'm going to use this to formulate the partial fraction. Already in the previous video, we explained how to obtain your partial fraction and the types of partial fraction you can get depending on what? The denominator. So we're going to apply that knowledge from previous video. Now, how many factors do we have in the denominator? How many linear factors? 2. You know, linear factors means the power of each of these x here is what? 1. Now, there are 2 of these linear factors, so we're going to produce 2 simpler what? Fractions from it, partial fractions from it. So I select my arbitrary constant to be a and b. It's going to be a all over 1 of the denominator linear factor plus b all over the second one, that is the second denominator linear factor. Now, this one we're going to solve this. Generally, we go through the LCM method. Are you following? Just like I explained in the very first video when we introduced partial fraction. However, I stated in the previous video that GMATS 41 is introducing the unmarkers denominator closing method and the numerator free value method. Of course, that's what we're going to use here. Is that okay? Now, this denominator closing method works for all linear factors. How does it go? Please watch. I want to get my a there. So I said that a, I don't know. But the denominator of a is x minus 2. Then I'm going to ask myself, what value can I select for x here to make this whole denominator 0? Under polynomial, we did something where if you say x minus 2, this whole denominator should be equal to 0. Solve for x. X equal to 2, there's an answer. If I do x minus 2 equal to 0 and then solve for x, x will give me positive 2. So if you select x equal to 2 here, this whole denominator becomes 2 minus 2, which is 0. Take note. So on the basis of that, I will now say, let x be equal to 2. If x is equal to 2, how do I now get my a? It implies that a will now be equal to what I'm going to do. I want to close the denominator now. So I will come to this term I'm resolving. Are you following? And close the denominator of a that I am looking for. I've closed the denominator of a, which is x minus 2. So what do you see left there? 4x plus 9 all over x plus 1. That will give us the value of a. 4x plus 9 all over x plus 1. But we know that x is equal to 2 under this condition. So it implies that a will now be equal to 4 bracket 2 plus 9 all over 2 plus 1. This is going to give us 4 times 2 is 8. 8 plus 9 is 17. 17 over 3. So we've gotten the value of a based on the partial fraction there. We'll do similar thing for b. So I'm going to say that b I do not know. Now what do you think the value of x will be there for b? You go there, the denominator of b. What value can you select for x to make the whole denominator 0? You'll agree with me that if x is equal to minus 1, you know how to get that. X plus 1 equal to 0, then solve for x. If x is minus 1, this whole denominator becomes 0. So I will come over here and say, okay, to get b, let x be equal to minus 1. Come to this part of your question, that is a complex or algebraic expression whose partial fractions you want to get. Close the denominator of b. If I close the denominator of b here, well, what is left? 4x plus 9 all over x minus 2. And that will be the value of b. So b is equal to 4x plus 9 all over x minus 2. On the condition that x is equal to what? Minus 1. Is that not so? So we know that x is minus 1. So it implies that b will be 4 into minus 1 plus 9 divided by minus 1 and then minus 2. If you work out this, 4 times minus 1 will give us minus 4. Minus 4 plus 9 is plus 5. So it's going to give us over minus 3 under here. So everything will be minus 5 over 3. And that is the value of b. Our problem is solved. Therefore, we now have to go back to what we are asked to resolve in the partial fraction. 4x plus 9 all over x squared minus x minus 2 is equivalent to, remember, the partial fraction we formulated for this is a all over x minus 2, b all over x plus 1. So what is our a? A is 17 over 3. So that's 17 over, that 3 will come as denominator here. So in place of a, you put 17 over 3. The 3 is denominator, so it's going to multiply x minus 2. Then what is our b? B is minus 5 over 3. So this b, minus 5 over 3, that minus will change this plus to minus. So it's going to be minus 5 over 3. Once again, that 3 will come down as denominator. It's going to multiply x plus 1 there. So this is our result. Or, and this is our result like I said, or we can still rewrite it as 4x plus 9 all over x squared minus x minus 2 is equivalent to, what is common to these two terms here? 1 over 3 is common because you have over 3 here, you have over 3 here. So I can write it as 1 over 3, open bracket, 17 all over x minus 2, then minus 5 all over x minus x plus 1. So this is another alternative way of writing the result. So remember, test your ZPD, your zone of proximal development, using this question. Follow the same format and say if you'll arrive at the correct answer. Now let us look at the second question here on the board. We have to resolve x plus 2 all over 4x squared minus 25 into partial fractions. At the end of this, you have to test your ZPD by resolving 3x minus 1 all over 16x squared minus 4 into partial fractions. Is that okay? So let's do this together. The first, we have x plus 2 all over 4x squared minus 25. Once again, take note that the denominator is a quadratic expression. Of course, it's difference of two squares. So I'm going to rewrite this to be x plus 2 all over. This 4x squared can be written as 2 squared x squared. And then this 25 can be written as 5x squared. So if this part is giving us 2 squared x squared, it will produce 2x minus 5. Where the 5 comes from this 5 squared. And then the second part will be 2x plus 5. Is that okay? So that's the concept of difference of two squares. Might be given a squared minus b squared. It's equivalent to a minus b and then a plus b. Any one of them can come first. Is that okay? Now having said that, we can now resolve this term into partial fraction. It implies that x plus 2 all over 2x minus 5 and then 2x plus 5 is equivalent to, the denominators here contains two linear factors. So it's going to produce a all over 2x minus 5 and then plus b all over 2x plus 5. You see, the process is all the same. We're going to use the Omakars denominator closing method to obtain our a and b. Of course, if I come over there to get a, I do not know. Alright, so I will locate the denominator of a. If you make 2x minus 5 equal to 0 and solve for x, you are going to get that x is equal to, so let x be equal to 5 over 2. That's what it's going to produce for you. If x is equal to 5 over 2, this whole denominator will be equal to 0. Is that okay? So that gives us room to get the value of a. It implies that a is equal to, I will come to this part, it will be x plus 2 all over, I will close the denominator of a here, which is 2x minus 5. So I'll be left with 2x plus 5. But we already know that this condition is true if x is 5 over 2. So the value of my a will now be equal to, I'll go over to this and then substitute 5 over 2 for x. So this is 5 over 2 plus 2 all over the denominator 2 bracket 5 over 2 and then plus 5. Resolving this is going to produce 5 over 2 plus 2. If you find the LCM, alright, you can work that out. I've already explained in previous classes how you can easily add or subtract a fraction from a whole number. So this is 5 over 2 plus 2. In working out the LCM, it's going to be this denominator times this whole number, 2 times 2, which is 4. Add it to this 5 because this is plus. If it were to be minus, it would be this numerator minus this 4. Is that okay? So in this case, it will be 5 plus 4. And 5 plus 4 is going to give us 9 all over the denominator 2. Is that okay? Then that will be over. If you come over here, take note that these 2 will cancel these 2. Is that not so? If you open up the bracket, these 2 will divide these 2. 5 will be left. 5 plus 5 will give us 10. So eventually our A is 9 over 20. These 2 will come down to multiply 10. You get 20, okay? In terms of division of fraction. We'll repeat similar thing for B. So B, we do not know. And now if I go to the denominator of B and let it be equal to 0, you'll get x to be equal to minus 5 over 2. So let x be minus 5 over 2. That being the case, it implies that the value of B will be equal to, I will come to this term and then close the denominator of B, which is 2x plus 5. That will be left with x plus 2 all over 2x minus 5 will be left because I'm closing this. Is that okay? Closing this. What do? We substitute the value of x, alright, but x is equal to minus 5 over 2. So the implication is that B is equal to minus 5 over 2 plus 2 for the numerator. Is that okay? And then all over 2 brackets minus 5 over 2, then minus 5. Does that make sense? We're going to work out this. Once again, the denominator here times this whole number is going to produce 4. So minus 5 plus 4 is going to give us minus 1. Is that not so? Then all over. Come to the denominator. You notice that these 2 will again divide these 2. You'll be left with minus 5. Minus 5 minus 5 will give us minus 10. So what do you see as the value of B? B is equal to 1 over 10. I guess the problem is solved. Is that not so? All we now need to do, please, this numerator is over 1. It's over 2 rather. The numerator is over 2 because we meant to divide by 2 here. So this is actually 1 over 20. 1 over 20, that's good. 1 over 20, alright? If we work out this, minus 5 over 2. 2 times 2 give us 4. Then minus 5 plus 4 give us minus 1 over 2. Then all over minus 10. Okay, so these 2 will multiply this 10 to give us 20. The negatives we cancel out. So let me cancel them out. So we've obtained our A and our B. We can now go back to the partial fraction we formulated. Look at the question we are solving. X plus 2 all over 4x squared minus 25. Okay, so that's going to be equivalent to, take note, the partial fraction we formed was this. So what's the value of our A here? 9 over 20. So in place of A, I'll put 9 here over 20. That over 20 will come down as a denominator. Then open bracket 2x minus 5. Then B plus, B is positive, so it will be 1 over, the 20 once again comes down as denominator, multiplies 2x plus 5. So this is the result, okay? That's the result. We can still choose to write it in the format, observing that over 20 is common to both of them. So we can say, or x plus 2 all over 4x squared minus 25 is still equivalent to 1 over 20 is common. So you factorize it out, 9 all over 2x minus 5. Then plus 1 all over 2x plus 5. And this can also be an alternative answer to that. Please test your zone of proximal development with this question. In the next video, we shall pick questions in which we treat other types of denominator.